Okay, so multiplexers, they are another important logic design element which we generally use, and they are quite important because we can use for various different operations, and we can also use it for logic function implementations, which we are going to see in a minute. Now, what is a multiplexer? Let's say I have got two roads, okay? And that roads are actually joining into one, which is going to combine into one road. Okay, and we have got two cars or buses, whatever you want to call them, with my drawings. Okay, now these two are driving in a different roads, but at some point, they are going to end up over here. Now, they may crash. So we need some kind of logic over here, like it's not a typical traffic light, but it can be a two-way logic, like when it is red, the one side will pass. So let's say road, let's name them. Let's rate road A and road B. And when it is orange, road B will be passing. Okay, and this is, let's say, road Y, and we are actually making a choice over here. We are making a selection which will cause these cars, or the whatever you want to call them, not to crash. Okay, so we are actually selecting a particular input over here, and we generally call this a select line, select input or select line. Now, how does this is operating? Let's say I have got a select input, input A, input B. We can derive a truth table for that, and we just have one output, which is Y. So three inputs, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So now, as we have got a binary logic over here, and as we are using two inputs, which are coming, or two rows, A and B, and we can say that when select is red, or when select is 0, the output will just have A, and when select is 1, the output will have B. Okay, so I'll make that orange. So in this case, when select is A or 0, that means output is going to be whatever we have got on A. So 0, 0, 1, 1. This is what A is got. So that will be the data. And when select is 1, we have got the output as whatever we have got on input B. So 0, 1, 0, 1. And this is what we have got in the end. Now, this is the truth table of the relationship. We can optimize this. We can derive the kernel map for three inputs, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, and select AB. Okay, now 0, 0, 1, 1, 0, 0, 1, 1, and then 0, 1, 0, 1. So 4 is 0, 5 is 1, 6 is 0, 7 is 1. Then these two can be combined, which will give us an expression for A, which is S prime dot A, and this will give us a combination for B, which is S dot B. So we can say that Y is when S is 0, it's A, or when S is 1, it is B. And that's the multiplexer function. So I can use that. So I'll just rewrite it. S prime A or S B. So two AND gates and an OR gate, which will give us Y. This is A, this is B. S is going in, and this is inverted, and it fits in over here. So this is the typical implementation of a 2 input, 1 output, which we call it 2-to-1 multiplexer or MAX, whatever you want to call over there. So they just use I0, I1, I use A and B. It's the same thing. There's nothing different at that point. Now, the logic symbol for a multiplexer is, this is Y, 0, 1, the select line, and A and B. This is a typical symbol that we use for a multiplexer. Now, we can also extend this multiplexer where I can have 4 inputs, A, B, C, D, and 1 output Y. Now, if I have 4 inputs, and if I want to choose one of those at a time, that means I need 2 select lines, because 2 to the power 2 will give me 4 possibilities. So S1, S0, so when both are 0, it's going to select A, 0, 1 selects B, 1, 0 selects C, and 1, 1 will select D. And this is a 4-to-1 multiplexer. And it's actually a condensed truth table. Now, you can see the implementation over here. By the way, one important thing with the multiplexer, the multiplexer circuitry can be divided into 3. So this part is actually decoding. When S is 0, is one of those activated. When S is 1, the other one will be activated. 2 AND gates are acting like an enable. Okay, so this is actually enabling the inputs. And then these are combining all together to have one function. And 4-to-1 multiplexer, you can have actually 26 entries with these combinations. And we just condensed into the 4 as they are important. So schematic is, again, we have got the decoding part, the enable part, and then we have got the combine. So this is decoder. It looks like a decoder. S0, S1, one of the lines are activated. And then when this line is activated, its input 0 is enabled. When this one is activated, input 1 is enabled. When this one is activated, input 2 is enabled. So decoder circuitry, enable circuitry, and combine them, you will get a 4-to-1 multiplexer. Okay, so 4-to-1 multiplexer is a combination of a decoder, enable, and combine gates. Now, if we want to summarize it, condensed truth table, when S is 0, I0. When S is 1, it's I1, depending on this configuration. It can be other way around as well, but this is a typical use of it. The Boolean function, let's move down, but this is Y is equals S prime I0 or S I1. And the question is, if we want to build multi-bit signals to select from 4-bit buses, how do we do that? So this is actually telling us that we have got a 4-bit bus. Let's say this is our multiplexer. Where 4-bit bus is 3 down to 0. Okay, and let's say this is I0 and this is I1. Oh, sorry, let's do it the other way around, 0 and 1. Now this is I0, this is also 3 down to 0. This is I1 and this is also 3 down to 0. And of course we have got the select line. Now The operation is same as 2 to 1 max. When s is 0 and when s is 1, which we are considering, it's going to be y 3 down to 0, and this is going to be I0 3 down to 0, and this is going to be I1 3 down to 0. Okay, so this is how we are getting it. Now, in order to implement it, as we have got 4 of those, 4-bit of those, we are actually need 4 tiny 2 to 1 maxes in order to implement it. Each one is representing one of the y outputs. So y0, y1, y2, and y3. This is what we have got inside of that. And the select lines are all similar, which is going to give us, I'll put it over here. And this is I0, 0-bit, I1, 0-bit, I0, 1-bit, I1, 1-bit, I0, second bit, I1, second bit, and I0, third bit, I1, third bit. Okay, so you can see the implementation actually over here, that with 4 2 to 1 multiplexers, we can actually have a 4-bit buses. Another challenging thing is, or it's not a challenge actually, but an alternative way of implementing it. How can we implement the 4 to 1 max using 2 to 1 max? 4 to 1 max, as we already said, it has got 4 inputs, 0, 0, 0, 1, 1, 0, 1, 1, A, B, C, D, and 2 select lines, S1, S0, and Y. Now, how can I implement that using 2 to 1 max? Now, 2 to 1 maxes, 2 of those are going to be connected to select 1, okay? And when select is 0, select 1 is 0, this is A, and this will be B, okay? Because these are activated over here. When select S1 is 0. And when it is 1, it's C and D. Now, as I have 2 outputs, I have to combine those outputs with 1 2 to 1 multiplexer as well, and this will be S0. And this is also 0, 1. So when it is 0, 0, it's A. When it is 0, 1, it's B. When it is 1, 0, it is C. And when it is 1, 1, it's D. So this is how we can implement 4 to 1 multiplexer using 2 to 1 multiplexers. By combining 3 of those, we can have 4 to 1 multiplexer. You can have the complete expression, same as this one. S1, S0 prime is A, or S1 prime, S0, it's B, or S1, S0 prime, it is C, or S1, S0, it will be D. And that's what this expression is actually. And this is the implementation of it. So this is how we are using a multiplexer. Let's say I want to just give you an example of a typical application of it. Let's say you have got an ALU, okay? In ALU, you have got arithmetic unit, okay? And you have got logic unit. Arithmetic unit does addition and subtraction. Logic unit does AND or NOT operations, let's say. Now, you have got one output from the ALU. This is an ALU. Now, you either choose arithmetic operation output or logic operation output. And you just need to use a multiplexer over there, which is coming out as a separate input, as a control input. So when S is 0, that means I want to get an output from the arithmetic unit. When S is 1, I want to get an output from the logic unit. This is a typical application of multiplexers. And inside of the processors, we have many of those because we have got lots of controls. We have to do those controls with these select lines. Okay, so another important application of the maxes are actually implementing Boolean functions. Now, we can actually implement Boolean functions by using logic gates, which we already seen that in chapter 3 and chapter 2, chapter 3, and also at the beginning of this chapter. But we can also use maxes. So how are we going to do that? Now, if you consider this Carnot map, we can actually combine those, and we can get an expression for Z as an output, which is A prime, B prime, or A, C. Okay, these two are giving us this expression, A prime, B prime, or AC. Now, we can actually use this and we can derive the truth table. Okay, now how many inputs do I have? I have got 3 inputs, A, B, C, and Z. Now, as we are using 3 inputs, we are going to get 8 possible combinations: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now, this is important because I just need to map this into a truth table. I'm just doing some kind of reverse engineering over here in order to find out my Z outputs. Now, we already know the Z outputs actually here. So it's 0, 0, 0. This is going to be 1. 0, 0, 1 will be 1. 1, 0, 1 is 1 based on this. And 1, 1, 1 is 1. And the rest are just zeros. Now, in order to implement this using multiplexer now, first, I have to decide which variables are going to be used as a select line and which variables are going to be used as a data lines. Now, depending on the multiplexer type as well, this is important. So if you want to use 4-to-1 multiplexer, let's say, I need 4 inputs, 2 select lines, and 1 output. So I have to think about 2 select lines. Now, the easiest way of doing this is when I look at the truth table, if I choose A and B as a select line, okay, I can easily get these combinations. When A is 0, B is 0. When A is 0, B is 1. When A is 1, B is 0. And when A is 1, B is 1. I can easily get those. And then data line will be based on C. Okay, and I have to find the relationship between C and Z. So how is that possible? Now, when A is 0, B is 0. So let's say this is AB as a select line. When A is 0, B is 0, the data line, C is 0, Z is 1, C is 1, Z is 1. So this is just giving us constant 1. So I can have the first input 0, 0, which is going to give us constant 1. And by the way, this is Z. Then, when it is 0, 1, C is 0, Z is 0, C is 1, Z is 0. This is giving constant 0, so I can have 0 over there. And 1, 0, C is 0, Z is 0, C is 1, Z is 1. This is actually giving as exactly C, so I can have C over there. And the last one, which is 1, 1. When both inputs select lines are 1, C is 0, Z is 0, C is 1, Z is 1. This is also C. So I can see that this can be implemented as a function with a multiplexer, A and B as an input, and the inputs are select input, and the inputs are 1, 0, CC. So this is a typical implementation of a logic function. We can do more different examples, but I want to leave that for a live session. So if you have questions to ask as well, you can ask me at that time. And at the end of this chapter, which we are having now, there are a couple of exercises, exercise 1 to 7. You can try them by yourselves, as you can see from here. You can see the solutions, and I'll also solve these during the live lecture. Okay, that's all I want to say for this chapter. Thank you for listening.